Okay, let's take a look here. I want to, here's kind of the plan for the rest of the week and early next week, just to give you a little heads up here. One thing I definitely want to do, I want to respond to the test. I need a chance to kind of sit down and comb through the data a little bit, and I'm going to pick some problems, the ones that were it seemed like they were the most problematic, and if there's some stuff that seems to be generally problematic for the group, and there are going to be some, I know there will be a few that are going to be the problems that really caused people some issues. And we'll hit those again tomorrow and take a look at those. I want to do that as quickly as possible, but I also, I don't, in a class like this, I don't want you just spinning your wheels and trying to tread in water. So what I want to do today is I want to start pushing into the next level of material, and I get an assignment out there for you to sort of keep occupied with outside of class. And then tomorrow we'll take a look at the test, like I say, answer questions about that. The practice tests, I'm going to leave those out there for you. And then on Monday, we'll be in the lab, and I'll kind of push people off. And I think most people, well, the majority of people in this class are probably going to elect to want to redo the test, even if they did well. I'll only give you your highest attempt, and so I'll open it up again for 2 more attempts on Monday. And then if there are, I know that there are in a few cases there's people that either aced it or did well enough that maybe they don't want, they don't feel the need to. And that's great. That's more power to you. That way, at least you'll have some work to spend lab time on. So, does that make sense? That's my strategy here. So what I want to look at today, this is really a big deal. Today we're gonna take the jump into calculus really for the first time. This is what we've done is we've cultivated the skills and the tools to now start moving forward to talking about calculus. But what we've done so far really honestly hasn't been calculus. What makes it calculus versus non-calculus? Well, I think you'll get a real sense of that today. Okay, the problem I want to look at, this is called the tangent line problem. And this is there are two big topics in the calculus that you will study for the next couple of years. And they are derivatives and integrals. We say differential calculus studies the derivatives and the application of derivatives in integral calculus. That's the following step. But before we get to integrals, we got to talk about derivatives because they're related. Now, the way we approach this is we're just going to look at a curve, f, and f could be anything. It's just totally general here. We're not going to pin it down. So there's our function f of x. It's nice and curvy. And what we want to do here is we want to talk about rates of change. Okay, now if I'm going to pick some arbitrary x value, we'll just call it x, what are the coordinates at that point? If my function is f and this is x, how would I write that ordered pair? I'll get you started. X, say it again? X, well, I could say xy.
F of x.
Okay, or in this case, f of x. X, f of x, right? I'm going to increase my x value, once again, by some arbitrary amount. We're not going to pin it down. We'll call it delta x. And delta might sound a little funny to you right now, but delta is a big deal in calculus. Delta, it's just a capital Greek D, and it's pronounced, well, what it equals is change in. You know how to pronounce it, just delta. But that whenever you see delta something in physics or in calculus, it's always talking about a change in a quantity or a change in a variable. So when we say delta x, it just means it's changed by some amount, and at least in the figure on the board here, it's that much, but it could be anything. It's a variable amount. And so doesn't that make the x coordinate here then just our starting amount x plus delta x? So what's the ordered pair here going to consist of? What are the coordinates going to be? If this is x, this amount is delta x. X plus delta x. And what's the value of the function going to be there? Yeah, it's going to be the value, and that's exactly, it's just going to be, we're just gonna evaluate the function at that x value, right? X plus delta x. So it's f of x plus delta x. And I could even write those y values in here. I just drawn these little horizontal bars. And so there's f of x plus delta x. And if we want to talk about a rate of change, all we're really doing here, that's just a slope, isn't it? And that's been hammered home probably, for many years now, that all a slope is a rate, right? A rate of change of quantities. And so this blue line here that connects these 2 points, would you agree that that blue line is nothing more than a representation of the slope through those 2 points? Okay, that's an average rate of change. And so we could call this, we call that line, by the way, a secant line. Okay, if it's a line through 2 points that's representing an average rate of change, it's a secant line, and the slope of that secant line would be what? Okay, good. So it's all it is, and remember, a slope is just delta y over delta x, right? And that's our way we really want to think about it. I know you guys are used to that old slope formula that involves y1s and y2s, and that's great. But really, an easier way to think about that is whenever you're talking about a slope, it's just change in y over change in x, and that's the best representation of a slope, right? Delta y over delta x, and that's all the calculation that we're doing here is. How much is y changing? Well, it's going from this value to this value. So the change is f of x plus delta x minus f of x. We can just make a little slope triangle here, right? So there's our slope triangle, delta y. Just f of x plus delta x minus f of x. And look, we already have this label. It's just delta x. Right? X plus delta x minus x is just delta x, right? So that's the bottom of our slope triangle. And so I need more room for that, all right. I'm going to put that down at the bottom. So the slope of the secant line, and this is what we call the difference quotient in calculus. This is a big deal. You'll see why here in a second. And that's useful. If we want to know the average rate of change, that's what we do. And you do this all the time without even necessarily thinking about it. For example, let's say that you're traveling from here to Hermiston. And Hermiston is how far away? 30 miles? Something like that? Let's say it takes you 30 minutes to get to Hermiston. Okay? So really, if we were to graph this, we're looking at displacement, displacement. Yeah, here, I guess, right, displacement here, how far we've traveled, and time along this axis. And we could graph our journey that kind of tracks our speed, but really all we're interested in if we want an average rate of change is change in y over change in x. The change in distance was 30 miles, the change in time was 30 minutes. What's the slope of our secant line? Well, okay, in this case, what would it be? 1 mile per minute, I guess. That was, no, hold on, 30 miles, 1 mile per minute. If we turn that into miles per hour, what would that be? 60. So our average speed was 60 miles per hour. Make sense? And you do that all the time. That's useful. Okay, that's calculating an average rate of change, total distance over total time. But let's say that we, let's say we want to know how fast we were going when we go by, what's some landmark on the way to Hermiston that we'd all be familiar with? That. When we go by the trees. Okay, there you go. Okay, there you go. So when we go by those, does that guarantee we're going 60 miles an hour? No, it doesn't at all, does it? This is a broad description, an average rate of change. It's not what we might call an instantaneous rate of change, right? It doesn't tell us much about that at all. Now, what might our strategy be, though, if we wanted to maybe more accurately document how fast we're going when we go by one stretch of road? What could we do? Any ideas? But our speedometer's broken, let's say. Yeah.
It's dangerous. You can't drive.
There's the obvious answer, yeah.
You can't drive with a broken speedometer.
Any ideas? What could we do? Okay, here's an idea. How about if we pick 2 points maybe that aren't 30 miles apart? What if we pick 2 points that are, say, a mile apart, right, instead? And we time it over that mile, and we find out that over that mile, it turns out that it takes us 70 seconds to go that mile. Okay, so then we're going, we could calculate, I don't know what that's gonna be, we could calculate how fast we're going over that mile, right? That's pretty good. Does that guarantee still, though, that that's how fast we're going when we go by that tree? Not really, because there still could be fluctuations within that mile. So what might we do to even improve on that? Make it smaller, right? Measure the time it takes to go a smaller interval where the car's not going to be changing so much. Make sense? And in that way, we could gradually, we could kind of whittle this thing down to where we could get pretty accurate estimates of how fast we're going, right? That's calculus. That's what we do with calculus in a sense, because this is the strategy that we're going to employ when we want to do something different and maybe more impressive than this. The next goal is we want to come up with the slope of not a secant line, but a tangent line. We want to come up with the slope of the curve at that point right there. Okay. Now there is, prior to Newton and Leibniz coming up with the calculus, people tried, but they couldn't really come up with an adequate way of doing that. But that's what differential calculus does for us. So pictorially, here's what we're adding. Okay, so that's probably not exact, but you get the idea. That's supposed to be, oh, that's not close, is it? It's got to come down a little bit. It's got to come up. You get the idea. That's supposed to be my tangent line. What's the definition of a tangent line? You probably never heard this, but what is the definition of a secant line? We said was a line that's connecting two discrete points and getting an average rate of change. What's a tangent line doing instead? Okay, it's connecting, it's only hitting the curve, or intersecting the curve at one point, at least locally. I mean, if this curve flips back this way up here, incidentally, it might intersect the curve again, but in the neighborhood of the point of tangency, it's only intersecting once, right? Okay, now, probably there's a little more to it than that, though, because I can draw you an example that meets that criterion, but is clearly not a tangent. You gotta add one piece to this. So here's my function f. I guess that's not a function, ignore that part over there. And I wanna draw a tangent line right here. Is that a tangent line? Because it only intersects at one point. No. Okay, something else is missing from our definition. And this is one that's hard to capture. This is the part that was so hard to capture mathematically. What else are we doing that we're not, it's gotta be more than just intersecting the curve at that point. What else is that red tangent line?
So maybe the slope of the tangent line is the same as the slope of the instantaneous slope at that point.
Bingo. Okay, that's it. Now that's weird. Think about that. We're talking about the slope of the tangent line matching the slope of the curve. But have you ever in your life thought about a slope of a curve before? Slope has always been a word that we've associated with lines, right? And that makes sense. I mean, a slope is defined to us as change in y over change in x. And those are characteristics of a line, right? Not a curve. So that's pretty strange, but that is the right answer. For this red line to be a tangent line, it has to intersect the curve, just so we could even say I want to graze the curve. That's a bad math word. We should say intersect, but it really is, in a sense, grazing at that one point. And the slope of the curve is matching the slope of the line. Now, how can you capture that? Well, one way to think about it, and you guys will have no problem with this because you have the video generation, you've seen this stuff a lot. Just kind of make a video game out of this and zoom in. What's going to happen to this if I just gradually zoom in on that point of tangency? What's going to happen to the curvature of the black function as we get closer and closer? It gets bigger and bigger. Yeah, it's going to flatten out, isn't it? Right? In the same way that if you observe the Earth from the moon, you can block it out with your thumb. So it looks pretty curved. But if you're standing in a wheat field in Athena, it looks, you'd be hard pressed if you didn't know a little thing or two about science to prove to somebody that the Earth is not just completely flat, right? Because you're so close to it, you're so zoomed in, that the curvature is all gone. from your perspective, right? And so it's the same kind of idea here. If we just zoom in on this thing, eventually, wouldn't you agree? And I'll put up a little, we can watch this visually here at some point, but I think you can kind of just imagine this. If we zoom in on this, as the frame of the screen or whatever closes in on that point, you're gonna see the curvature disappear, and the red tangent line and the black curve are gonna look identical, right? And so that's capturing, it's much more sophisticated than just a line now. The slope of the curve is what happens if you remove the curvature. If you zoom in really far and it starts to look linear, then that's capturing the essence of the slope of the curve. Does that make sense? Okay. So that's the goal then. That's calculus. That's what we want to do, is we want to move from kind of this wimpy average rate of change that's just a little algebra to calculus, which is an instantaneous rate of change. We want to be able to determine what is the slope of the curve at that point. And that's like saying, what would my speedometer read? Okay? What is my instantaneous speed as I'm driving in the car? Okay? So, how do we do that? Well, you have the tools. Now think about this process, and we kind of already outlined it. Our strategy for trying to come up with a good approximation of our speed during our trip to Hermiston is really the same strategy we're going to employ up here with our function. If I want to come up with the rate of change, instantaneous rate of change of the function at this point x, we got to kind of do the same thing. And now just think back to what we've talked about for the last couple of weeks. Is there a mathematical tool that allows us to, to make that interval on the road shorter and shorter and shorter? Arbitrarily short. We don't have to make it a mile or 100 meters or 10 meters. Okay, take a second, just at your tables, and hash this out. See if you can come up with an idea that explores a group. So Trevor, you got to join somebody. Lone wolf over here. Okay, so ideas. What can we do? What can we do here? Just throw something out here. We'll get specific in a moment, but any ideas how we could use the tools we've kind of worked with here to shorten that interval? What do you think? Okay, there's a limit involved, and that's what I'm looking for, exactly. Why not take a limit, right? I mean, yes, ma'am.
The sandwich thing that you talked about.
Okay, the sandwich thing, sure. And that actually is sort of behind the scenes involved in this too. The limit thing is big here because we don't want to limit ourselves. Poor choice of words. We don't want to constrain ourselves to just having a pretty good approximation. I mean, if we're driving down the road and we say, okay, we're going to go over a 10-meter interval, that's pretty good. How much is a car traveling at freeway speeds going to change its speed over 10 meters? Not much, but it's not perfect, is it? I mean, it would a little bit. And we want something that's exact. We don't want something that's just pretty good. And so why not take a limit as that interval approaches what? So I guess here's the other piece of this. If we want to get that really good approximation with our stopwatch, we're going to travel a certain distance and time it. That distance is, we're trying to just shrink that distance down, right, to get it more accurate. Well, if we invoke the idea of a limit, we're going to take the limit of that distance, call it delta x, as delta x approaches what? 1? We could 1, but then even 1, that's 1 meter, still that's a distance. 0.1? That's better. But remember, we're not actually plugging a number in, we're just approaching something. Let's say it again. 0, yeah. And that means 0 plus, I guess, doesn't it? But we're just going to approach 0. We want this interval effectively to approach 0. And look what we're doing when we do that. We're just going to drag this point as delta x shrinks towards 0. Look what happens. This point up here is just going to shrink back along the curve, and eventually it's going to push towards just overlapping with the other point. And those 2 points just merge into 1, and it becomes a tangent line. The secant line becomes a tangent line, right? Make sense? Okay, so what's that going to look like in terms of the calculus then? Well, really all we're doing is we're starting with, I guess I need to go to the next page. We're just starting with the slope of a secant line, right? There's the slope of the secant line. And to get the slope of the tangent line, we're just really taking the limit of this as delta x goes to 0, right? That's our strategy. Okay, and so then our definition of this slope of the tangent line would just be this expression evaluated in the limit that delta x goes to 0. And that is a derivative. That's what we call a derivative. It's the instantaneous rate of change of a function. Okay. Now we're going to come up with some great tricks. There are some rules for taking derivatives that apply to specific functions, and it makes it a lot quicker. But for now, our only mechanism for calculating a derivative is by applying this limit. Okay, so let's, and for today, my only goal for today is that we can get to a point where we can just understand kind of what this means and maybe how to apply it to a function. Okay, so let's try that. I'll just pull up an example, and I'm purposely going to pick one that's from your book, so you can refer back to this. You don't have to take notes on this. You can just refer back to this in your book. Let's take, this guy's good. We'll do that. Okay, so if we want to find the slope of the line tangent to the function f of x equals x squared plus 1 at x equals negative 1. How about, let's do that. So I could graph this, and let's just, for now, let's just quickly do that, just a little sketch here. What's this going to look like, this function x squared plus 1?
Parabola.
Okay, parabola, just a normal parabola that's been transformed in what way? Okay, good. Yeah, picked up by 1 vertically. So just something like that, right? And so if we wanted to find the slope of the tangent line at x equals negative 1, that's that point of tangency right there. Is the tangent line going to be positive or negative? Negative. It's just going to look something like that, right? So that's what we're going to find. We're going to find the slope of the curve, essentially. Same thing. And you understand that means the same thing. We can say those interchangeably. I can say the slope of the tangent line to the curve, or slope of the curve. Really just means the same thing. At x equals negative 1. Okay, so we have our derivative now. We just have to apply it. So my recommendation is, in fact, it's not even a recommendation. This is why I want you to do it this way initially, because this is a good habit to get in. You always start general and work towards the specific. So we'll start with the general derivative every time, and then we'll just plug in the specifics and do the algebra that goes with it. Okay, so here's where we start. That's built in. Okay, so step 1. Okay, and I won't give you the notation yet. I don't want to do that. That's extra confusion. So we'll just call it m tangent. Okay, step 2. Apply that to our function. What is our function? F of x equals x squared plus 1. Okay, so if our function is f of x equals x squared plus 1, what is f of 2? 5. And you get that from 2 squared plus 1, right? What's f of a? Okay, what's f of b? Okay, what's f of x plus delta x? Okay, good. The quantity x plus delta x squared plus 1, right? You got, and that's the pattern, right? All this is telling us, this function, is for any input, these are the operations I'm doing to that input. So if the input is a sum of 2 terms, that's all right. I'm just going to square the sum and then add 1, right? Make sense? So this part right here, I'm going to color code this, how about? So this part right here is just going to become, oops. You just told me that's going to be the quantity x plus delta x squared plus 1, right? Make sense? And I'm going to put brackets around that just because it's one thing, right? That's f of x plus delta x minus f of x, which we already know. That's just x squared plus 1, right? And gosh, I forgot something there. Forgot to write limit. That's key. Can't do that. Forgot it in both places. That's really bad. See what I did? What I always tell you not to do. You gotta make sure you're writing that limit notation down. So the slope of the tangent line equals the limit of all this stuff. And by the way, once again, it's called the difference quotient. And I'll write that down. This is the difference quotient. Okay? The difference quotient is just delta y over delta x. We're taking the limit of the difference quotient. Okay? In math, that's the label we give that. And it's just all over delta x as delta x goes to 0. Now that, if we just kind of flip into, yes ma'am?
Aren't you supposed to distribute the negative to x?
Oh, yep, I need to do this, don't I? Yeah, you're right, yeah, sorry. I gotta put that in brackets too, very good. Okay, so now this looks an awful lot like stuff you've been doing. At this point, we can kind of just switch into calculus mode or algebra mode, however you want to think of it, and do some simplifying. What's your instinct here? I mean, right now, if we try to evaluate directly, we get 0 over 0. I'm gonna get x squared plus 1 minus the quantity x squared plus 1 over 0, right? So at this point, it means more work. But the algebra, or the pre-calculus, or whatever you want to call it, that we've been doing kind of informs that process. What do you think you need to do here? I can see why that would be not a bad suggestion. But typically we did that when we had square roots in there. Right, when we were trying to rationalize, using that rationalizing technique. This one here, what do you think? And they're all gonna, the good news is they're all gonna kind of look like this. So once we've done this once or twice, it gets pretty, pretty mundane. What do you think? Notice I've got the x plus delta x quantity squared there. Okay, and so you see that's kind of a problem a little bit because this delta x is still inside of this factor and this one down here is not. So, any suggestions? What do you think? It could be a bad suggestion. What do you think our ultimate goal is here? Okay, yeah, to cancel the factors that are causing that indeterminacy, to cancel the delta x's. So somehow I've got to be able to get a factor of delta x on the top, right? Okay. What do you say we just kind of clean things up, just simplify the top and see what happens? By that I mean we could distribute the negative, we could expand this binomial, we got x plus delta x squared, right? Let's try that. So if I expand that binomial, what is the quantity x plus delta x squared? True. And if I FOIL that out, what do I get? Okay, good, 2x delta x, good, plus delta x squared, plus 1. If I distribute this negative sign, I get minus x squared minus 1, right? All over delta x, as delta x goes to 0. Now I'm out of room, I gotta go to the next page, but this is where all the action happens. This is kind of a self-cleaning process, you'll find. It always works. Okay, what do you see there? Is there any horizontal cancellation?
Yeah.
Yeah. Yeah, well, it looks like the 1's cancel, and what else?
X squared.
The x squareds. Okay, I want you to notice now, the terms that canceled were all what we might call the negative terms, the terms that don't have delta x's in them. They all canceled. All the terms that we're left with have delta x's, right? So if I rewrite this, you won't normally want to even take the time of rewriting this, but I just want to make this abundantly clear to you. What we're left with on the top is just a 2x delta x plus delta x squared over delta x. And the idea is
Factor out delta x.
factor out the delta x's. Is that, yeah. Leaving me with what on top?
So with delta x.
And there's what Elizabeth predicted is going to happen. We're going to get the delta x's to cancel, right? Okay, so we get this vertical cancellation. That's good. Now that we've canceled the delta x's, what do we do?
Plug it in.
Plug it in. Now we try to evaluate directly again, right? Because that's, remember, the 0 over 0 just meant more work. We tried evaluating directly, and it told us to do more work. We did the work, and now this is what we're left with. And so that final delta x is just going to go to 0. And what's our answer? 2x. Oh man, now that's big. You may not appreciate what we just did there, but we have x's in our answer. See, that's awesome. Because now we don't even have to pin down. Have we even plugged in yet? This is just so cool. We haven't even plugged in yet. Right, oh, there, I wrote over the top. That x equals -1. We haven't even applied that yet, have we? That's nowhere, we've never even specified where this is happening. All we've done is just said our function in general is x squared plus 1. We applied that limit of the difference quotient, right? And we got an answer which we might call a derivative, slope of the tangent line, but we've never pinned it down. We could put any x value we want to now. We've come up with a completely new function based on the original function, whose job it is to predict the slope of the curve, the derivative function. And I think that's why it's called a derivative, because it's derived from the original function by this process. So the slope of the tangent line is equal to 2 times x for any point on the curve. Okay? Now the notation we use for that is this. And there's some other notations too, but for now I'm just going to show you this one. We put a prime on the original function, and that means we've changed it by taking the derivative. So now it's f prime of x is 2x. And so if we want to calculate the slope of the tangent line at the point x equals 1, what do? Plug in -1. Good. So slope of the tangent line at x equals -1 is just f prime of -1, which is -2, right? Okay. So now what if I want to come up with the equation of the tangent line at x equals -1? And this is just going back to like Algebra 1 stuff, right? What are the two ingredients of the equation of a line? What do I need?
Slope and
Okay, slope and a y-intercept, hopefully. But in general, maybe I don't luck out and actually get the y-intercept, at least initially, I can always find it. But in order to find the equation of a line, and maybe write it in slope-intercept form, I need what two things? A slope and a point, right? And then I can always plug that stuff in and do a little algebra and come up with, rewrite it in slope-intercept form. So I have a slope. If my original function is x squared plus 1, can I come up with a point? What do I do to find the point? I'm trying to find the slope of the tangent line at x equals -1. So I've got the slope of the curve using calculus. And now we don't even need calculus for the rest. How do I come up with that point of tangency? What's the point where the tangent line is actually intersecting the curve? X is -1, we know that. How do I find y, I guess is what I'm asking.
plug it in.
Yeah, plug it into the function, right? Y is just f of x, right? So y, in this case, our specific y is f of -1. F of -1 equals what? 2? Okay. So isn't that just telling me then that the point of tangency is at -1, 2? Right? And so now we come up with the equation of the tangent line. Because remember, and I know this is pretty juvenile, but I just want to make this point because we do a lot of this stuff. I maybe introduce some new words. I don't know if you've heard these terms before, but this is important. M and B in this case are what we call parameters, right? This is the equation of a line in two. Well, how many lines could I graph in the XY plane? How many different lines are there? More than a lot. Infinite, right? I mean, there are an infinite number of lines that we could graph in the XY plane. Each one of those is unique, and each one of those is specified by the values of those two parameters, right? And so, if we can just dial in a certain value of M and a certain value of B, we can nail down a line. So all we have to ever do is just come up with the values of those two things. One of them is given to us. We know that M is, what was it, -2?
Well,
We just need to find B. And what's our strategy then for finding B if we know a point? Oh, it's -2.
yeah. One.
What's always our strategy for finding B? Okay, plug in a point. Now, how come? And once again, I know you know the process pretty well, but I want to make sure that we're also thinking about that in terms of, conceptually. Why is it that I can plug in the point -1 and 2? Okay, graphically, because it's a point that's on the line, right? Think of a line or a curve or anything like that as really just being the locus of points. That's just a fancy math word for the collection or the set of points that satisfy the original equation, right? So a line is really just an infinite string of these little points that are strung together like beads on a necklace. And at any one of those points, the coordinates of which are known, represents one of those beads. Now, thinking of that in terms of the function, we know that if this is a solution of the function, it has to satisfy the original equation, right? Does that make sense?
Yeah.
And so that's something that I know you guys have, at times in your careers as mathematicians, short as they are, you've thought about those two concepts, but it's really important to kind of merge those into one. That a solution to an equation, like an ordered pair, represents a point on a curve. Okay? That's useful to us because when we want to do things like find simultaneous solutions of equations, we want to solve systems of equations, and we're going to get into some of this stuff, like maybe hard equations, not just linear stuff. Maybe we've got a system of quadratic equations. We want to find the solutions. Really, all those are shared solutions, right? So they're points of intersection. See what I'm getting at? We'll come back to all that stuff, but I want you kind of thinking along those lines. So then we could just plug in the -1 for x, the 2 for y, and then we have everything in that equation nailed down except b. So we'd end up with 2 equals -2 times negative 1, did I do that right? Oh, I guess I did. Yeah, I did. Plus b. Okay, and so 2 equals 2 plus b, what's b gonna be? 0. I don't know if I drew my original picture very well, but where is my picture? Next page? Well, I didn't. That line should have gone through the origin. I mean, if I had drawn it to scale and correctly, that one would have gone through the origin. Okay? Make sense?
Yeah.
All right. Oh man, I want to show you another thing, but that's probably. Okay, here's what I'm gonna do. Last thing, and then there's a lot of stuff today. Tomorrow we can go work, answer a couple questions over the test, and then we'll go to the lab. You guys can work on some things. Here's the one thing I want to remind you of, because when you're doing these problems, as you might imagine, I picked a pretty easy one because it's just a square, right? It's a polynomial, a second order polynomial. But what if that had been instead, we had been trying to find the line of tangency for something like f of x equals x to the 4th, or x cubed, or what if there'd been a higher power of x in there? Can you kind of see, thinking ahead in terms of your strategy, that when you plug in the derivative formula, oh darn it, where am I going with this? There's so much stuff up here, can't keep track of it all. When you, I guess back on this page, when you do this to it, right? When we end up expanding this binomial, this x plus delta x to a power, it was pretty easy to do when we squared it. We all know how to, we know that expansion pretty simply, but would you know off the top of your head, if that were, say, an x to the 4th, how to expand that out? Without having to go through the tedium of x plus delta x times x, of actually going through and doing the algebra, which we don't want to do. Do you know how to do that? Okay, I gotta show you the trick. This is a great trick. Here's the trick. It's called Pascal's triangle. Remember Pascal's triangle? Here's Pascal's triangle. There you go, good. So it's just ones along the outer slopes of the triangle. And the intermediate numbers are just going to be always the sums of the above two numbers, right? Two numbers that feed it. So there is no in-between number here, but there is here. This one is going to be the sum of those two. So it's a 2. This one is going to be the sum of those two, so it's a 3. You get the idea.
Yeah.
So then this one would be
6.
Okay? What does that have to do with binomial expansions? Everything. Okay, all this is telling us is if we assign each of these rows of the triangle a number, those are just the powers of the expansion. So the top row is 0, second row is 1, and so on. 2, 3, 4. And you wouldn't want to do this, beyond, say, 5 or 6, it's probably, this is too much work, and then we'll just use the binomial expansion formula. But for, we don't do that very often. Mostly we're just doing stuff in here. And so this is pretty useful. So what this is telling us then is that x plus delta x, for us, I'll use those because that's the one you're going to be using, to the 4th is equal to, these are the coefficients of the terms. So I know I'm going to get 1 times something plus 4 times something plus 6 times something plus 4 times something plus 1 times something. Well, what are the somethings? Okay, here's how you think about this. If the power of the binomial, this is a 4th order expansion, right? So I know that when I FOILed this out, what's the biggest power of x going to be? 4, okay? The sum of the two exponents is always 4. It's just going to start with all the weight shifted towards the x and eventually shift. So all the weight is shifted to the delta x. So this first one is just going to be an x to the 4th, delta x to the 0, which we don't even need to write because we'll put anything to the 0 power. 1, okay? Plus 4, x to the 3, delta x to the 1, plus 6, x squared, delta x squared. You get the idea.
Oh, yeah.
Plus 4, x to the 1, delta x cubed, plus 1, delta x to the 4th. X to the 0. But
Why is
see how that works? Question? Kendall? Oh,
okay, why?
well, go ahead.
Why is the delta x like goes up and then the like x's go down?
Just because that's arbitrarily the way that we choose to write it. We could have written it the other way, but we're just saying because the x came first, the x is the one that will start having all the, when we FOIL it out. See what I'm saying?
Yeah.
But it could have been, it wouldn't really matter. The order of the terms
Okay.
isn't really going to impact the actual answer.